The first cosmic velocity is necessary for a celestial body for stable motion in a circular orbit. The second cosmic velocity allows any material object to permanently leave a powerful gravitational field. For Earth, they are about 8 and 11 kilometers in every second of time. Small celestial bodies are completely devoid of an atmosphere due to the extremely low value of the second cosmic velocity.
Welcome. Today we will conduct a rigorous analysis of cosmic velocities. Now, these are the fundamental speeds that govern all motion within a gravitational field, determining whether an object remains bound to a planet, enters a stable orbit, or breaks free entirely to travel into interstellar space. Our entire discussion is predicated on a foundational principle, the law of conservation of energy. In any closed system, the total energy, which is the sum of an object's kinetic energy of motion and its potential energy of position, must remain constant. So, these critical velocities we're examining are derived from the balance between an object's kinetic energy and its gravitational potential energy. We will proceed through this analysis in a structured manner. First, the concept of cosmic velocity itself. Then we'll move to the governing equations. We will perform a calculation for planet Earth, then a comparison across the solar system. And finally, we'll discuss the consequences of gravity's pull. So, let us begin by formally defining the two velocities that are the subject of our analysis. These velocities define orbital and escape trajectories.
The first cosmic velocity, or circular velocity, is the specific speed at which the gravitational force provides the exact centripetal force needed to curve an object's path into a perfect circle around a planet. Any slower, and the object would fall back to the surface. Any faster, and the orbit would become elliptical.
The second cosmic velocity, more commonly known as escape velocity, is the minimum speed required to break free from a celestial body's gravitational field entirely. At this velocity, the object's kinetic energy precisely equals its gravitational potential energy, allowing it to travel infinitely far from the body.
Okay, now we will examine the mathematical formalisms that describe these physical concepts. This is the mathematics of gravitational fields.
The formula for circular velocity is a function of three variables: the gravitational constant g, the mass of the central body m, and the body's radius r. As you can see, a more massive or more compact body requires a higher circular velocity. Now, the formula for escape velocity is nearly identical. However, note the critical inclusion of a factor of 2 inside the square root. This seemingly small difference has profound implications. Placing them side by side directly reveals the mathematical relationship between the two. Escape velocity is always greater than circular velocity by a factor of the square root of 2, which is approximately 1.41. Let us now ground these abstract equations by performing a calculation for our home planet Earth. This will be a practical application of the theory. By substituting the known values for Earth's mass and radius, along with the gravitational constant, into our equation, we can solve for the first cosmic velocity. The calculation yields a result of approximately 7,905 meters per second. So the first cosmic velocity for Earth is approximately 7.9 kilometers per second. This is the speed required for an object to maintain a low Earth orbit, like the International Space Station. And subsequently, by multiplying 7.9 kilometers per second by that factor of 1.41, we determine Earth's escape velocity to be approximately 11.2 kilometers per second. This is the velocity that probes like Voyager had to achieve to begin their journeys out of the solar system.
Now, let us apply these principles across the solar system. This will help us understand how these velocities vary with planetary scale and how mass and radius dictate gravitational binding.
As this table clearly illustrates, the required velocities are vastly different across celestial bodies. They range from a fraction of a kilometer per second for an asteroid like Vesta, all the way up to over 600 kilometers per second to escape the gravitational pull of our Sun. Note Jupiter's immense escape velocity of over 60 kilometers per second. This is a testament to its enormous mass and its consequently deep gravitational well. It truly is a gravitational monster, making it extremely difficult for any object to leave its grasp.
Finally, we will explore the profound physical consequences that arise from these velocity thresholds, from the practicalities of rocket science to the exotic physics of black holes.
Well, the relationship between energy and velocity is not linear. It's quadratic. Energy is proportional to the square of velocity. This means the energy required to achieve escape velocity is double that required for orbit. That 3.3 kilometer per second difference for Earth has immense implications for rocketry and fuel consumption. Escape velocity also acts as a kind of atmospheric filter. Bodies with low escape velocities, like our moon, cannot gravitationally bind gas molecules. The thermal motion of these molecules is simply fast enough to exceed the escape velocity, so they drift away into space. Earth's higher escape velocity is what retains our atmosphere. Now, let us consider the ultimate speed limit in the universe, the speed of light, approximately 300,000 kilometers per second. This leads us to a final, critical question that pushes the concept of escape velocity to its absolute physical limit. What happens when an object is so massive and so dense that its escape velocity exceeds the speed of light itself? The answer, of course, is a black hole. This is a gravitational well so deep that nothing, not even a photon of light, possesses the requisite velocity to escape from beyond its event horizon. It represents the point where gravity becomes so intense that it traps light itself.
Thank you, friends. Strive for understanding and become wiser. See you soon.